Bernoulli's equation, this is what we're going to talk about now. Let's say that we have a surface at the bottom down here and we want to describe a pipe flowing through. But let me just go ahead and the definition is quite algebraic. But here we go. It says we can use these concepts that are introduced. Let me see, they say 3-point and fluid flow, and that's dealing with the continuity equation. We can use these concepts to derive an important relationship known as Bernoulli's equation, which is what we're about to talk about. And it relates the pressure, flow speed, and the height for a flow in an ideal fluid. Okay, so an ideal fluid is a fluid that's inviscous. It is inviscid, rather. And it's also incompressible. Okay, so let's go ahead and do this. So let's say we have ourselves a tube here. Next, we're going to draw an element of fluid. Okay, and this element has an area associated with it. And let me get to that real quick. I'm just drawing this element so far. And it has an area. We're going to call that A1. It also has a pressure associated with it. Thus, we have a force. And I'll draw that later. But it's an element. In other words, it has a certain amount of height or a certain amount of width to it. And that's going to be delta S1. So that is in meters. Area is in meters squared. So if we combine those two, if we in a product form, then we get meters cubed. So that'll be volume. So this is going to have a certain volume. And according to the continuity equation, this volume will be the same all the way through if we just consider this. No matter the thickness of the pipe or the how can I say, the thickness, I guess I could say that, but it's really the cross-sectional area. So this element will have a velocity, 1, and it'll also have a height, and we're going to call this y sub 1. Cool? So if we just continue right on, you'll see that this fluid is going to flow up, it's going to flow up, it's going to flow up. And then as it gets to a different section of the pipe, we'll have a different area, okay, and thus a different width. And that width is going to be delta S sub 2. Okay, so we'll just go ahead and color that in. All right, and this is going to have a certain volume, delta V, but that delta V is the same as the delta V down at the bottom. Okay, so the volume did not change. We have a velocity 2 at the bottom, and then we have a pressure that's acting back on this. And this is P2 times A2. Okay, so we'll also have that pressure down on the bottom, and that pressure will be P1. So the P2 times A2, that's actually a force. And then we have P1 times A1, that's going to be a force as well. So let's just continue right on. So this thing is going to have a certain height associated with it, and this is going to be Y2. So we have Y1 and we have Y2. If we look right here, we have Y1 and we have Y2. It's going to be up here. Okay, let me do that again right there. So let me just keep going here, and it's going to flow in this direction. So this is the direction of flow. All right, so the fact that we have fluid on the other side, of course, that's where that pressure is going to come from. Now we want to use the work energy theorem to describe or to derive Bernoulli's equation. So we're going to have delta K plus delta U, and delta K is our kinetic energy. It's the change in kinetic energy. Delta U is the change in potential energy in the gravitational field. So it's gravitational potential energy, and this is going to be work done by some other components. So this work can be from a pump, or it could be from a turbine. If it's from a pump, the pump is going to add energy to the fluid. If it's from a turbine, it's going to remove energy from the fluid. Okay. So let's continue on. Let's describe the work other. So work is just basically the net force times some displacement. Okay, in this particular case, we're not concerned about it being in the X or the Y or the Z. We're just going to say it's some displacement, and it's in this pipe. And you see that the displacement is right here. It's delta S for this piece, and then it's delta S2 for this piece. Okay, so let's continue right on. And so if we're going to describe work effectively, and there I am writing my pressure P1 down here. I forgot to put it there to indicate it. But it's really pressure times area 1. Okay, that's going to be this force. So there it is. That's the force. So let's go ahead and write this in. We have P1 times A1. That's our force, okay, acting on that plate, times delta S1. That is going to be the work, all right, done. And I'm calling it a plate, but done on that element of water or fluid. So this is going to be minus P2, which is at the top, times A2, which is our force, times delta S1. So that's going to be our work, okay? Yep. So I say where other and where, and I'll just let that go, and where. And I'm going to bring in our let me see what I'm going to bring in. Oh my gosh. And I could just go ahead and write this in, but it's basically where delta V is just going to equal to A1 times S of 1. It's also going to be A2 times delta S2. So we can change our work other to being P1 times delta V minus P2 times delta V. So we can rewrite this. We can just say P1 minus P2 times delta V. This is going to be our work other. And we will substitute this back into our work energy formula. The next thing, so that's going to go here. So we're now about to treat our delta U. And I'll just go to a new page for that. So delta U, or U, is just equal to mgh. Okay. So in our case, we're going to have delta U is equal to m times g times y2, and of course this is a vector, minus m, well actually it's not a vector, sorry about that, it's just the magnitude, minus mg y1. So we need to, since we know that density is just equal to m over the volume, this implies that m is just equal to rho times delta V. And we're going to go ahead and put that into this equation. So delta U is going to equal to rho times delta V times G times Y2 minus rho delta V times G Y1. So we can pull all of that out. So this will end up being rho times G times delta V Y2 minus Y1. So this is going to be our delta U. And that is this portion of this equation, of this work energy theorem. So now we're going to treat the kinetic energy. And remember, kinetic energy is just equal to 1/2 mv squared. So if we look at delta K, this is going to be 1/2 times m1 times v, no, not m1, M2 times V2 squared minus 1/2 M1 V1 squared. So again, we're going to use our relationship for the density. Okay, and so now we can substitute this back into this equation. We know that the mass isn't going to change. The mass has to remain the same. Even though I wrote M1 and M2, it's going to remain the same. So let's go ahead and do this. Delta K equals to 1/2 times rho delta V. The fluid is the same. The volume is the same according to the continuity equation. V2 squared minus 1/2 rho delta V, V1 squared. So we can just pull all of that out. 1/2 rho delta V, V2 squared minus V1 squared. This is our third equation that we're going to put into our work energy formula. So I'm just going to go back to that real quick. I'm going to put all of those into this equation. So let's go ahead and do that. We have delta K plus delta U equals to work other. And I just want to substitute those things into that equation. And we'll start off with the first one. We have 1/2 rho delta V times V2 squared minus V1 squared. Okay, and then we're going to have our potential energy, which is just rho times delta V times G, and this is going to be Y2 minus Y1. Okay, and this is going to equal to the pressures, P1 minus P2 times delta V. Now what do we have here? We're just going to divide the entire equation by delta V. The volume doesn't change throughout. So what do we end up with? We end up with 1/2 rho V2 squared minus V1 squared plus rho G Y2 minus Y1 equals to P1 minus P2. So what we're going to do now is we're going to put everything that's related to 1 on the left-hand side and everything that's related to 2 on the right-hand side. And we'll come up, well, this is Bernoulli's equation, period, right here. We could stop right here. We can organize it any kind of way we want, but this is Bernoulli's equation. But we're going to put it in a form that's nice and neat. P1 plus rho G Y1 plus 1/2 rho V1 squared equals to P2 plus rho G Y2 plus 1/2 rho V2 squared. And this is a more common way to look at Bernoulli's equation. So Bernoulli's equation, pressure, flow speed, and height in a fluid. Pressure, flow speed, and height in a fluid. Subscripts 1 and 2 refer to any 2 points along a flow tube. So Bernoulli's equation may also be written as P plus rho Gy plus 1/2 rho V squared is equal to a constant. Okay? Basically, what I gather from that is that it's always going to be constant throughout that tube. No matter where you go or no matter which section you take, there'll be a constant flow or pressure in that tube. Okay? All the way throughout.